Acids and bases definitions.
In this presentation, we will accomplish a lot. We will define the three acid-base theories and then learn to distinguish the acids and bases based on these three different definitions. We'll proceed to define strong and weak acids, conjugate acid-base pairs, identify the weaker, stronger acid-base conjugate pairs in an hydrolysis reaction, and then define the terms amphoteric and polyprotic. Now, let's start now with the oldest acid-base theory, which was developed in 1884. It says that an acid is a substance that delivers hydrogen ions into the water solution. Base delivers the hydroxide ion into the water solution. A generic dissociation for acids and bases are represented here, and there are several problems with this theory, but the most important one is that it only allows for one kind of base, a base that has an hydroxide ion in its structure. And this is a problem because ammonia, being a base, does not contain hydroxide ions, but it still acts like a base. So, in 1923, a new theory was developed, which is now our working theory of acids and bases. Is known as the Bronsted-Lowry acid-base theory. So when we talk about an acid or a base today, we typically mean the Bronsted-Lowry acid or base, unless we specify otherwise. So what does it say? An acid is any compound that donates a proton. A base, on the other hand, is any compound or ion that accepts a proton. So, as you can see from this diagram, from this graphic, when I have hydrogen monochloride being dissolved in water, hydrogen monochloride acts as an acid because it donates a hydrogen ion to water, and in doing so, having lost a hydrogen ion, becomes the chloride ion. And on the other hand, water acts as a base because it accepts the hydrogen ion, and then becomes the hydronium ion. Please know that the hydronium ion and the hydrogen ion are the same thing. They, in the past, when we were talking about acids, we just mentioned the hydrogen ion, but really when an acid does provide the hydrogen ion, it really causes the formation of a hydronium ion. And this is much more closer to the truth. In actuality, we have the hydronium ion does not exist by itself, but we believe it exists in a group of 4 or 6 hydronium ion in a cluster. But just represented it now as either a hydrogen ion or as a hydronium ion is good enough, and we choose either one or the other depending on our convenience, whatever is convenient to us to show. They are equivalent. So the Bronsted-Lowry theory expands the number of potential acids, because any species that contains a hydrogen with a +1 oxidation number can be an acid. Acids can be, therefore, neutral molecules, such as hydrochloric acid that reacts with ammonia to form an ammonium ion and a chloride ion. They can also be positive ions, such as now the ammonium ion reacting with the hydroxide ion to provide the formation of ammonia and water. Or they can be negative ions. It could be the dihydrogen phosphate ion that donates a hydrogen ion to water and becomes the monophosphate ion, and water becomes the hydronium ion. It also expands the number of potential bases, because a base now can be any species that contains one or more lone electron pairs. And therefore Bronsted bases are identified from knowing their Lewis structure. Because, why is it that way? Because the only way to accept a proton is to form a coordinate covalent bond to it, which means that the base must provide both electrons, and it can do so through an electron pair. So all of these species, all of these substances can be bases, Bronsted bases, because they all have lone pairs. Okay, let's see what we have learned. Which of the following will be considered bases according to both the Bronsted-Lowry and the Arrhenius definitions? What about ammonia? Well, we already talked about this. Ammonia does not contain an hydroxide ion, so it cannot be an Arrhenius base. So this is not an answer that works. What about hydrobromic acid? Could this be a base? Well, certainly not an Arrhenius base, but it certainly could be a Bronsted-Lowry base, because if you draw the Lewis structure, you'll see that it has lone pairs of electrons on the bromine. What about barium hydroxide? Well, can it be an Arrhenius base? Definitely. It has an hydroxide ion. What about a Bronsted-Lowry base? Definitely too, because if you draw the structure, the Lewis structure, you'll see that oxygen has lone pairs. Hydrofluoric acid, Bronsted-Lowry base? Definitely. Just like hydrobromic acid. Fluorine has lone pairs. Arrhenius base? No way. Does not have the hydroxide ion. Potassium hydroxide? Definitely both. So the answers are C and E. Okay, see if you can do this. Which of the following compounds can be Bronsted acids and which can be Bronsted bases? Figure this out. Pause the presentation first and then come back. Okay, so if you draw the Lewis structure of all four of them, you'll see that all can be both Bronsted acids, because they all contain a hydrogen ion with a +1 oxidation number, and they all can be Bronsted bases because they all contain a non-bonding pair, electron pair. Okay, let's go on to a different topic. We have discussed this though already to some extent. We have discussed the difference between strong and weak acids. And if you remember, we said the strong acids are the ones that completely dissociate into hydrogen ion and the corresponding anion, because the bond between the X atom, whatever atom that is that holds the hydrogen, is very weak, and the hydrogen can be picked off. Whereas weak acids do not lose hydrogen ions readily, because there is a strong bond that holds the hydrogen together with to the X atom. On the other hand, strong bases are the ones that attract hydrogen ions strongly, and weak bases have a weaker attraction for hydrogen ions, of course, all in accordance with the Bronsted-Lowry theory. What might be actually be better to say, if one were to kind of think about it a little bit, instead of saying strong or weak acid, it might be better to say fast or slow acting acid, because a strong acid puts all of the hydrogen ions in solution immediately, causing a reaction to be much faster, whereas a weak acid releases the hydrogen ions initially only a small amount, and then it keeps releasing them as the hydrogen ions are consumed, but that makes the reaction weaker. Excuse me, not weaker, but the reaction makes the reaction slower. Let's continue now with our definitions. What are conjugate pairs? They are acid-base pairs that differ by one proton in their formula. So what do we mean by that? Well, if ammonia in this case is the base, because look at the end result on the right side of that equation, ammonia has picked up a hydrogen ion and it has become the ammonium ion, so has accepted a hydrogen ion, so it's a base. Well, that means that the ammonium ion is the conjugate acid, because if we were to look at the reaction going backwards, then the ammonium ion will be giving up the hydrogen ion in order to become ammonia. On the other hand, water is the acid in this case, because it provides the hydrogen ion and it becomes the hydroxide ion, which it is the conjugate base. Or if we were to look at the reaction in reverse, then hydroxide ion would be the base, the water would be its conjugate acid, and of course the ammonium ion would be the acid, as we already have discussed, and ammonia would be the conjugate base. Now identify on your own the conjugate acid-base pairs for these two hydrolysis reactions. By the way, every reaction with water is known as an hydrolysis reaction. Pause the presentation, come back when you're done. Okay, so in the first case, acetic acid and its anion, corresponding anion, are acid conjugate base pairs. Water, in this case, accepted a hydrogen ion, became the hydronium ion, so water in this case acted as a base and produced a conjugate acid. Methylamine, in this case, it is the base, because if you look at the product, it accepts a hydrogen ion. Water in this case is acting as a acid because it donated a hydrogen ion to methylamine, and therefore the hydroxide ion is its conjugate base. Let's look now at the relative strengths of conjugate pairs. We say that a strong acid has a relatively weak conjugate base. Why? Alright, let's look at this hydrolysis reaction between a generic HA acid and water. Now, if HA is a strong acid, it means that it gives up hydrogen ion readily. Consequently, it must mean that the conjugate base, the A-, must be a really weak base, weaker than water, because it must really have little affinity for hydrogen ions. Otherwise, the HA would not be completely dissociated into ions. Otherwise, there would be some molecular HA still sticking around. Hope this makes sense. If it doesn't, just stick with me. It'll make more sense as we go on in our discussion. So, here we go. If HA is a strong acid, okay, then it must mean that the conjugate base must be the weaker base of the two bases around. The other base is water, right? Water must be the stronger base in this case, okay, because it does accept hydrogen ions and forms the hydronium ion. And the hydronium ion, obviously in this case, must be the weaker acid, okay? Otherwise, it also will give up hydrogen ions and form water. But notice that the equilibrium in this situation is completely on the right side of the equation, because we have what we call a strong acid, something that completely dissolves into ions. Alright, so let's look at a weak acid. We say that a weak acid has a relatively strong conjugate base. Why? Well, if HA is a weak acid, meaning it donates a few hydrogen ions to water, then the conjugate base, the A minus, must have therefore high affinity for hydrogen ions, and therefore it must be a stronger base than water. Otherwise, okay, the HA will be completely dissolved, but it's not, because it's a weak acid. Okay, so weak acid is something that only is partially dissolved. So if HA is the weaker acid of what's available here, then it must mean that the conjugate base must be the stronger base of water, simply because although water does form the hydronium ion must also be the stronger acid. Why? Because, same reason, because by being the stronger base, the A minus, the conjugate base, causes a lot less ion formation, dissociation, in other words, of HA. And the hydronium ion, being the stronger acid, donates hydrogen ions to the conjugate base, the A minus, and forms water. So, as we know, the equilibrium in a weak acid situation is on the left side, because most of a weak acid remains in its molecular form. I do recommend that at the end of this presentation you do look at the animations that are in the other presentation folder that follows these presentations, to help you get this point cleared up if it's not clear by the time we're done with this presentation. In any case, even if it's not clear, please look at the animation. It's very useful. Okay, let's go on and let's talk about strong and weak bases. So, a strong base must have a relatively weak conjugate acid. Alright? Reverse conversation of what we did before. If A minus is a strong base, readily accept hydrogen ions, then HA must be an acid that's weaker than water, because it doesn't give up hydrogen ions readily. So if A minus is the stronger base, then HA must be the weaker base. And HA must be the weaker acid. Weaker than water, because by being the stronger acid, it's maintaining the it's picking up the it's losing hydrogen ions completely in order to form the hydroxide ion, which in this case is the weaker base. So a weak base must have therefore a relatively strong conjugate acid, given that if B is a weak base, in other words, it accepts very few hydrogen ions, then the BH plus ion must be a stronger acid than water, because it readily gives up hydrogen ions in order to keep the equilibrium on the left side. So if B is a weaker base, then this must be the stronger acid. Consequently, this must be the weaker acid, and the hydroxide ion, the conjugate base of water, must be the stronger base. Here is a summary table of acids and their corresponding conjugate bases in terms of increasing acid strength as compared to increasing base strength. Notice that the stronger the acid, the weaker the conjugate base, and vice versa. Okay, you guys identify the conjugate pairs in this hydrolysis equation and their relative strengths. Pause the presentation, come back when you're done. Okay. Now, here is the conjugate pairs. In other words, ammonia and the ammonium ion are the base conjugate acid pair. The water and the hydroxide ion are the acid conjugate base pair. Now, why do I have the ammonia as the weaker base and the hydroxide ion as the stronger base? And also why do I have the water as a weaker acid and the ammonium ion as the stronger acid? Well, there are two ways you can look at solving this problem. Number one, you could say that ammonia, being a weak base, because it's not on the list, must have a relatively strong conjugate acid, the ammonium ion, which consequently must be a stronger acid than water. After all, the equilibrium in this reaction rests on the left side, and therefore there are not too many ions in solution. There's more molecular ammonia and water present on the left side. Or you could say, well, following what I just said, actually, equilibrium favors the reactants. It must mean that the ammonium ion is a stronger acid than water, given that it donates most of its hydrogen ions to the hydroxide ion to form ammonia and water. Okay, try your hand at this problem. This is the amino radical ion reacting with water to form ammonia and the hydroxide ion. The problem says the equilibrium favors the products, so determine which one is the stronger base, the amino radical ion or the hydroxide ion. Come back when you're done after pausing the presentation. Okay, well, because the equilibrium favors the products, meaning that we have much more hydroxide ion in solution than the amide ion, that means that the hydroxide ion must be weaker at picking up hydrogen ions and forming water. Whereas, since equilibrium is on the right, that means we have a whole lot of ammonia, more ammonia than the amino radical ion present. Therefore, it must mean that the amino ion radical must be the stronger base, since it has picked up a whole lot of hydrogens from water to form ammonia. I hope this is clear. Okay, so here's a pattern for solving the conjugate pairs type of problems. You want to identify the side that is favored by equilibrium. For me, knowing the list of strong acids or bases from a statement indicating which side favors equilibrium, from percent ionization, because if the problem says that going forward the reaction is 20% ionized, then you're dealing with a weak acid or base. If it says it's 100% ionized, then you're dealing with a strong acid or base. Or from the value of an equilibrium constant, such as Kc, Ka, or Kb. Ka and Kb we'll address shortly in the next presentation. And once you identify the side that has the that is favored by equilibrium, then that is the side that has the weaker conjugates. Now, let's define amphoteric and polyprotic. Amphiprotic or amphoteric are species that can act both as either acids or bases, meaning they can either accept or give up protons. Now, water is a perfect example of that. Polyprotic, on the other hand, polyprotic acids, on the other hand, are species that can lose more than one hydrogen ion. So anything that is diprotic means that there are 2 hydrogen ions in the structure. Triprotic, 3 hydrogen ions, as you can see from these structures. Let's now look at the third acid-base theory, the Lewis acid-base theory, which was proposed at the same time the Bronsted-Lowry theory was proposed in 1923 by G.N. Lewis, an American physical chemist, professor at Berkeley. He said that an acid is an electron pair acceptor, whereas a base is an electron pair donor. Okay, so you can recognize from here that the hydrogen ion would be the electron pair acceptor and the hydroxide ion would be an electron pair donor. So in the Bronsted model, the hydroxide ion would be the active species because it accepts a hydrogen ion to form a covalent bond, while in the Lewis model, the hydrogen ion is the active species because it accepts the pair from the hydroxide ion to form a covalent bond. Okay, so ammonia, which is not an Arrhenius base, can be, however, both a Bronsted-Lowry base and a Lewis base. Because as a Bronsted-Lowry base, it can accept a proton, but as a Lewis base, ammonia can donate the electron pair to species other than hydrogen ions. So there are reactions. There is a reaction such as this, such as ammonia and boron trifluoride, where nitrogen provides its two electrons, its lone pair, and it's known as the Lewis base. And the boron trifluoride here, accepting the electron pair, is known as the Lewis acid. As you can see, the Lewis acid theory expands even further the species that can be classified as acids. Okay, so how is it that ammonia and boron trifluoride react? Well, in the Lewis theory, an acid-base neutralization occurs when a coordinate bond is formed between a Lewis acid and a Lewis base. What is a coordinate bond? Where it's a covalent bond where both electrons, the lone pair, comes from one atom. Now, this works this way, this particular reaction. You have boron trifluoride, that is a trigonoplanar molecule that has a 2p orbital. Why? Because the boron is sp2 hybridized. And so, boron trifluoride now acts as an electron acceptor, in other words, a Lewis acid, of the ammonia lone pair, electron pair. And that's how this reaction works. Okay, let's see if you can predict whether these two species can act as Lewis acids or Lewis bases or both. Pause it and come back. Okay, well, silver, if you draw its electron configuration, has an empty 5s and 5p valence orbitals that allow it to act as a Lewis acid or electron pair acceptor. rather than a electron pair donor. Ammonia really has no empty valence orbitals, suggesting that it can only be a Lewis acid. In the appendix, I show you how you can explain non-redox reactions using Lewis acid-base theory. Now, this information just for your edification, and I'm not going to explain it, but I will dedicate a few seconds to each slide so you can stop and read it. We have come to the end of the presentation. If you have any questions, email me or reach me by other means.